In this example, we're told we have an air conditioning system in which air flows over some tubes carrying refrigerant R134A. So here's the air conditioning system. Air is coming in, it's flowing over this tube that I'm just kind of showing is going back and forth, and that carries the refrigerant. We're told the volumetric flow rate of the air. Let me write that down. So the Q of the air is 50 cubic meters per minute. We're also told the temperature of the air coming in, and so let's write that down. T air in, that's 32 degrees C, and the pressure of the air coming in as 1 bar absolute. Told that the air exits at 22 degrees C, so it's an air conditioner, so it's cooling down the air, and the pressure of the air coming out is a little bit lower as well, 0.95 bar. The R134A, we're told, is coming in with a pressure of 5 bar. So that's R134A coming in. And we're also told the quality of the R134A coming in of being 0.20. So we know it's in a saturated liquid vapor mixture phase. And then it exits with the same pressure. It's a pretty common assumption. It's not true really in practice. There's some pressure drop. So the pressure here will be a little bit lower than the pressure there. But for, first cut engineering model, assuming that the pressure remains nearly constant along that pipe is okay. Okay, we make that assumption a lot in basic thermodynamics. We're also told the temperature of the R134A coming out is 20 degrees C. We're told to ignore heat transfer at the outer surface of the air conditioner, so what that means is the heat transfer across this boundary. There's certainly a lot of heat transfer between the air and the 134A across the tubes, but on the outer surface of the air conditioner there's very little heat transfer. We're also told to neglect kinetic and potential energy effects and determine at steady state the mass flow rate of the R134A and the rate of heat transfer between the air and the refrigerant inside the air conditioner. Excuse me. So when I look at this, I think, okay, first of all, this will likely be a first law type of analysis because we have some significant change in properties for the R134A in the air. So that it's very likely to include heat. The first law, certainly for part B, it will involve the first law because we're trying to find a heat transfer term. For part A, mass flow rate, of course, naturally you think of conservation of mass, but mass flow rate also shows up in the first law as well. Okay, so we're going to examine both. So the first thing I'm going to do is just do a very simple application of conservation of mass just on the pipe for the R134A. Okay, so if I drew a control volume that surrounds just the R134A pipe, and then let's go ahead and I'll write it all out here. So here's conservation of mass for the R1 for that first control volume. Since it's steady state, this term is 0. So that's 0 because it's steady state. Coming in, we have the mass flow rate of the R134A in. Going out, we have the m dot of R134A out. So what this tells us is the mass flow rate of the R134A is a constant. You could have figured that out pretty easily without kind of the more formal treatment like I did here, but I just thought I'd go through this the first time just so you could see it. So I'm going to call that mass flow rate just R134A. I'm not going to put the in and out subscripts because I know it's the same. And you can do the same sort of analysis for the air. Just draw a control volume that just surrounds the air, doesn't include the R134A. I'm not going to show that here, but it's the same idea, and what we'll get from that will be that the mass flow rate of air coming in will equal the mass flow rate of the air going out. And so I'll just call it mass flow rate of air. Okay, so it's the same kind of conservation of mass analysis. All right, so that's what conservation of mass tells us for each individual component. Now let me go ahead and apply the first law. Let's just see what that gives us. By the way, just so you know, we're trying to find the mass flow rate of the R134A, and the conservation of mass just tells us that it doesn't change between the inlet and outlet. So we need to try something else to figure out what that mass flow rate is. So that something else we'll try will be the first law. And I'm going to apply the first law to a control volume that surrounds the entire device, because that will bring in the mass flow rate of R134A. As far as the mass flow rate of the air, we can actually find that. Since we're given the volumetric flow rate and the temperature and pressure at the inlet, I can figure out what the mass flow rate is. I can use the temperature and pressure with the ideal gas law to find the specific volume, and with the specific volume and the volumetric flow rate, I can get the mass flow rate of the air. So that part I can determine. But the mass flow rate of R134A shows up in the first law, so I'm going to apply it here. So it's the first law applied to the entire air conditioner. So let's write out the whole thing, then we'll simplify it. There's a lot to write down, so just give me a minute. Okay, so there's our first law expression. Let's go ahead and simplify. The first term is going to be 0 because we're told that we're dealing with a steady state process. So the total energy within the control volume is not changing with time. We were told that there's no heat transfer across this outer boundary, so that term is going to be 0. So that's just a given. There is no power going into this box, right? So just in this is really just a heat exchanger, and there's no electrical power, no rotating shafts, no springs or anything like that. So that term is 0. So we're left with these total enthalpy flow rates coming in. So this is the rate at which total enthalpy comes into the control volume. This is the rate at which total enthalpy leaves the control volume. Remember that this term in parentheses is sometimes called the total enthalpy. It's just a shortcut way to talk about specific enthalpy, specific kinetic energy, specific potential energy. It just makes it a little easier to talk about. Well, we're told also in the problem statement to neglect kinetic and potential energy effects, so these terms will be 0. Right, so a lot of things cancel out here. And so what we're left with, when we simplify it all down, we're going to have, for the in, we'll have the air times its specific enthalpy coming in. We'll also have the mass flow rate of the R134A times its specific enthalpy coming in. So that's what's coming in. I'm evaluating this term. So here's the mass flow rate times specific enthalpy for the air coming in. That's right here. Here's the mass flow rate times the specific enthalpy of the R134A coming in, which would be right there. And then we have to do the same thing at the out. We have the air coming out and the R134A coming out, so we'll include both of those. So this will be mass flow rate of the air times the H of the air out minus the mass flow rate of the R134A times the H of the specific enthalpy of the R134A coming out. All right, and now we can group terms and rearrange to solve for the mass flow rate of the R134A. Okay, so this will look like the following. Okay, I'm just doing a little bit of algebra on this equation here. I'm just rearranging it, and we're going to get the following if I do all my algebra correctly. By the way, that should be an in there. Okay, so let me just take a quick look at that to make sure that all makes sense. Yeah, I think so. Okay, so this is how we're going to find our mass flow rate of 134A. So to find the mass flow rate of the air, I talked about this a moment ago. This will be the volumetric flow rate of the air divided by the specific volume of the air. And I'm going to do this specifically at the inlet, because that's where that information is given, right up here. This would be the volumetric flow rate of the air coming in. So I'm given the Q, or the volumetric flow rate coming in. Now to get the, I'm not given the specific volume coming in, but of course I can find that using the ideal gas law. So from the ideal gas law, the specific volume of the air in will be the gas constant for air times the temperature of the air coming in, which we're given, divided by the pressure of the air coming in, which we're also given. So we can do that calculation. And let's see, I did that calculation somewhere here. Let me go ahead and try to find the number for you. Yeah, this comes out to be, the specific volume coming in is 0.8754 cubic meters per kilogram, and that gives you the mass flow rate for the air of 57.12 kilograms per minute. It's actually a really big number for air. Okay, so that gives us the mass flow rate for air coming in. Now what we need to do is find the specific enthalpies for the air coming in and out. Well, again, we're treating air as being an ideal gas, so we know that for an ideal gas, let me write it over here. For an ideal gas, we know the specific enthalpy is a function only of temperature. And so we can use the ideal gas property tables for air to find out what those specific enthalpies are, because we're given the temperatures coming in and going out for the air. Right? So we can find those. So the air specific enthalpy coming in will be the specific enthalpy of the air coming in at the given temperature of, what is it, 32 degrees C. You'd want to convert that over to Kelvin, but you can do that, and you'll find that this comes out to be 305.2 kilojoules per kilogram, and you do the same thing for the air going out. I'm not going to show the lookup in the table. I think you've done enough examples, hopefully by this point, that you know how to use those ideal gas property tables to look up the values. So again, these come from ideal gas property table. Okay, so that gives us the specific enthalpies for the air at the inlet and outlet. Now we have to find the specific enthalpies for the R134A at the inlet and outlet. So let's start at the inlet. At the inlet, we're told that we have some quality. The quality is 20%. So I know immediately we're in a saturated liquid vapor mixture phase. So I can go ahead and use the saturated liquid vapor mixture table, organized based on pressure, because since I'm given a pressure here. And then I can calculate what the specific enthalpy is there, making use of the quality. Right? So the way that's going to work is the R134A, let me clean that up, R134A specific enthalpy at the inlet, it's going to be 1 minus the quality at the inlet. I'm not going to put the R134A anymore, just to save myself a little time writing. That times the specific enthalpy of the saturated liquid at the inlet, plus the quality at the inlet times the specific enthalpy for the saturated vapor at the inlet. And again, I find these quantities will come from the saturated liquid vapor mixture table for R134A at pressure of the inlet pressure of 5 bar. Okay, so again, it's a matter of looking this up in the table and doing the calculation. I'm not going to go through all the details of it, but I will give you what the values are. So that H of the specific, the specific enthalpy of the saturated liquid is 73.358 using the table that I had available. The saturated vapor specific enthalpy was 259.33 kilojoules per kilogram. And so the HR134A, the inlet comes out to be 110.55 kilojoules per kilogram. All right, so we're making progress. The last one we need to find is the specific enthalpy of the R134A at the outlet. Okay, so So at that one, what we're going to do is, so at the outlet, we're given both the pressure and the temperature. So again, what I'm going to do is go to the saturated liquid vapor mixture table for R134A. I'm going to look at it organized based on pressure, I think, since we're already using that table. And I'm going to compare the saturation temperature to the given temperature. And if I do that, what I'll find, I'll just mark it here, that the saturation temperature at that given pressure, that comes out to be 15.735 degrees C. So that's the saturation temperature for R134A at 5 bar. And you'll see that our given temperature, 20 degrees C, is larger than that. So since that temperature is larger, so let me write it here, since T out is greater than T saturation, that means we're dealing with a superheated vapor phase. Right, so then to find the specific enthalpy for the R134A in the superheated vapor phase, we have to use the superheated vapor table at the given pressure and temperature. So 5 bars and 20 degrees C, and what you'll get is that the R134A specific enthalpy at the outlet is 263.5 kilojoules per kilogram. So this is at P out of 5 bar and T out of 20 degrees C. Okay? So again, I'm not going to show you how to go through all the tables. We've done many examples like that along the way, so hopefully you know how to do that. All right, so once you have that information, we have everything we need to calculate the mass flow rate for the R134A. And so when you plug in the numbers for that, I end up getting 3.77 kilograms per minute. All right, so a lot of, we've made use of a lot of different things that we've covered in the course so far. We did conservation of mass on a couple of control volumes here to realize that the mass flow rate for the R134A is a constant, and then the same thing for the mass flow rate of the air. We applied the first law, simplified it significantly using some given assumptions, rearranged that to get an expression for the mass flow rate of the R134A, and then we had to calculate the mass flow rate of the air given the volumetric flow rate. We had to use the ideal gas law along the way to get the specific volume for the air at the inlet. Define the specific enthalpies. For the air, we use the ideal gas property tables. For the R134A at the inlet, since it's a saturated liquid vapor mixture, we had to use the quality to calculate that specific enthalpy. And then at the outlet, we recognize that we're dealing with a superheated vapor phase since the temperature there was greater than the saturation temperature, and so we used a table to find that. So a lot of different things that we made use of. Okay, so now the next part of the problem statement is to find the rate of heat transfer between the air and the refrigerant. Okay, so there's some heat transfer between this tube and the air, like the refrigerant in the tube and the air. So to do that, I'm going to draw a control volume that surrounds just the air, and I'm not very good at drawing that. But I'll try to sketch something out here. So I want to do a control volume that surrounds the air and doesn't include the tube. So it kind of goes around like this, goes around the box. I know this is very kind of messy looking, but basically it's just a control volume that surrounds the air. It's probably best if I just write it down in words. So using a control volume surrounding just the air in the air conditioner, apply the first law. And this is because I want to get the rate of heat transfer between the air and the R134A. So I want that control volume to surround, one of them. So I just chose to surround the air. And then I'm going to apply the first law because I'm trying to find the heat transfer. Okay, so let's write out the first law again. Again, there's a lot to write out, so just takes a moment. Hopefully you've memorized by now how to write out the first law. If you haven't memorized it just yet, it means you need to do more examples. Okay, so you want to get to a point where you just have it locked in your brain because you've done so many examples, it just comes naturally. Okay, so let's go ahead and simplify this first law expression for our control volume surrounding just the air. So again, we're dealing with steady state, so that first term is 0. The Q dot is what we're trying to find, so we leave that in there. There's certainly some heat transfer between the air and the R134A. There's no heat transfer between the air and the surroundings because there's a box. So what I mean by that is there's heat transfer between the tube and the air, but there's no heat transfer between the air and the box and the surroundings, right? Because the box was well insulated. There's still no work, no power being done here. We're still neglecting the kinetic and potential energy changes because we're given that. So then what we're given, so when we simplify this, what we're going to get is the following. 0 is equal to Q dot into the air plus the mass flow rate of the air times the H of the air at the inlet minus the mass flow rate of the air times the H of the air at the air's outlet. Okay, so then let's rearrange that to solve for the heat transfer. So this is the heat transfer into the air, what it is we're trying to find. And we're left with that. Okay, so now we need to solve for the heat transfer into the air. Well, we know all of these values, right? The mass flow rate of the air we calculated back here. The specific enthalpy at the outlet and the inlet for the air, we use the ideal gas properties tables to find those. So we have everything we need. So we can go ahead and plug those values in, and we get that the mass flow, the heat transfer into the air is minus 577 kilojoules per minute, which means that there's energy leaving the air, in fact. So I'll just make a note here. Energy is leaving the air, which is what you'd expect for an air conditioner, right? It's leaving, energy is leaving the air and going into the R134A. That's how an air conditioner operates. Is you're trying to condition the air, you're trying to cool the air off, so you want energy to leave the air. So what you do is you bring in a refrigerant that's at a temperature that's much smaller than the air. You can see this up here, that air temperature coming in is 32 degrees C. The temperature of the refrigerant coming in was at its saturation temperature of 15 degrees C. And so there's going to be heat transfer from the air into the refrigerant. So the energy is going to leave the air and go into the refrigerant. So that will cool down the air. It reduces its internal energy. Actually reduces its enthalpy ultimately. But it takes energy out of the air, and then the energy goes in from the R134A. The energy goes into the R134A, converts it from a saturated liquid vapor mixture into a superheated vapor at the outlet here. We determined that was in a superheated vapor phase. So I did this part of the problem with the control volume surrounding the air. You could do the exact same thing using a control volume surrounding the R134A, and you would get the same answer. Okay, you'd still get 577 kilojoules per minute leaving the air and going into the R134A. All right, so this is a good example because it makes use of a lot of different topics that we've covered in the course so far. And so hopefully, make sure you go through it and understand all the little parts. We'll end it there.